So hi everyone, this is this set of questions set 4 of 2507. We start to analyze BJT circuits and the BJT device itself. So for question 1, we have BJT current relations. So for part A, we have an NPN BJT is found to have its alpha ranging between 0.95 to 0.99, and we need to find the corresponding variation for beta of this transistor. So for this particular problem, so for part A, we know that beta is equals to alpha divided by 1 minus alpha, right? So if we have alpha in the range of 0.95 to 0.99, we just have to substitute in this equation, and then we figure out that beta, it varies from 19 up to 99. Okay, so this is for part A. Now for part B, we have an NPN BJT that has a base current uh, of 50 microamperes and an emitter current of 5.05 milliamperes. We need to find the collector current, beta, and alpha. So in this case, let's assume it's working in the active mode, right? So for active mode, then we know some relationships between currents. So first we know that the collector current is equals to the emitter current minus the base current. So this gives us those 505 milliamperes minus the 50 microamperes, and that's equals to 5 milliamperes. Okay, now from this current values, we know IB, we know IC, we know IE. We can calculate the beta and alpha. So for beta, we know that this is the ratio between IC and IB. Okay, so if we substitute 5 milliamperes divided by 50 microamperes, this gives us 100, right? And then for alpha, we know that's the ratio of IC divided by IE. And if we take 5 milliamperes divided by 5.05 milliamperes, that's something around 0.9901. Okay, so those are the answers for part B. Now for part C, we have an NPN BJT when measured at room temperature. So this information is useful because it gives us the value of VT, right, for room temperature, which is usually 25 millivolts. So it has a collector current of 4 milliamperes, while it has a no-ideality factor of 1.2, and reverse saturation current, or like the saturation current, 1 nanoampere. We need to find the voltage across the base emitter junction, so we need to find VBE. So we know that part C, we know that VBE is equals to N times VT natural log of IC divided by IS. So if we substitute, let me see here, so VBE, yeah. So for NVTLN, we know that if we substitute this one here, we find VBE equals to 0.4561 volts. Okay, and if you want to know like what's the value of VEB, then it's just we just take the negative of that, so it's minus 0.4561 volts. Okay, just in case you just need to be careful about VBE and VEB. So if it is a BJT NPN transistor, right, then we have VBE on the equation for the current. Now for a PNP BJT, when measured at room temperature, has a collector current of 2 milliamperes and a base emitter voltage, so VBE of minus 0.66 volts. If the base emitter voltage is changed to minus 0.72, what would be the current through it? Okay, So in this case, we can calculate, so for part D, right? First, we need to calculate what's the saturation current for the standard case. So IS is equals to IC divided by exponential of VEB divided by Vt. Considering that its ideality factor is 1, so it's not given, let's assume 1, and Vt as 25 millivolts. So if we substitute here, we get 2 milliamperes divided by exponential of 0.66 divided by 25 millivolts, and that gives us around 6.84 picoamperes, right? So it's given VBE, right? Minus 0.66. So just remember to take the negative of that because it's a PNP. So here it's VEB, okay? Now that we know the saturation current, we can calculate the new collector current. So the new collector current is just IS exponential of VEB, the new value of VEB divided by the thermal voltage. So this is just 6.84 picoamperes times exponential of 0.72, right, positive value, divided by 25 millivolts. So this gives us a collector current of around 22 milliamperes. Okay, so that's it for problem 1.